Hello, my name is Bohdan Hlovatskyi and today I'll present our work, DeVos, Flow-Guided Deformable Transformer for Video Object Segmentation. This work was done during our internship at the Machine Learning Lab of Ukrainian Catholic University and was founded by ADVA. Video Object Segmentation is the task of segmenting one or more objects throughout a video given a ground truth segmentation mask for the first frame. The common approach is to distill the information from past frames into a feature memory storage and later perform a dense memory matching to identify objects on the current frame. One downside of the common paradigm is the dual learning requirement imposed on the network that is supposed to learn both semantic features and scene motion context. We argue that it's important to adapt regions with which we perform matching based on the specific query semantic properties to perform propagation robust to appearance, scale, and shape changes. Additionally, we propose to decouple motion and semantics during matching, adopting a global scene displacement field as an initial offset of the search region. To describe our method, let's consider a video sequence along with the annotation mask of the first frame. Our approach processes the frame sequentially, storing the predicted results in memory to inform future predictions. Firstly, we extract features from the current frame using a backbone encoder resulting in feature map IT. Subsequently, the feature map of the current image is compared with the memory frames to perform semantic matching and propagate the mask. Finally, the matching result combined with features from the encoder at multiple scales is fed into the decoder, which restores the object mask in its original resolution. Besides, we built our architecture on top of the AOT framework, which decouples long-term and short-term matching. As motion between consecutive frames is usually small, we can use this inductive bias to reduce the search regions for short-term matching. To understand how our memory matching is performed, one has to have some preliminary knowledge of deformable attention. Given a set of reference points and image features X, for each query and its corresponding reference point, offsets are learned to indicate the specific locations from which values and keys for attention should be sampled. These offsets are obtained based on the query features, ensuring that they capture and represent semantic information. Afterward, multi-head attention in its classical formulation is performed. To decouple scene motion context and semantics during matching, we propose an adaptive deformable video attention called ADVA. It has two stages, offset prediction for feature alignment and multi-head attention. As no motion information is injected in deformable attention formulation presented in DAT, the offsets should learn both semantic information and motion context. As the nature of movement is isotropic, in this naive formulation, query offsets would be forced to learn wind of attention for matching with previous frames. To mitigate this issue, we incorporate two subnetworks for offset generation based on queries and motions respectively. Such formulation allows learning sparse region to attend to each of the queries and can be naturally extended to high resolution as it's linear with respect to spatial resolution. Moreover, to benefit from the sparsity of the proposed attention formulation to its fullest, we propose to conduct semantic matches with the memory bank on multi-scale feature maps. Without BL30K for pre-training and MoZ for main training, our wideband DeVos L achieved state-of-the-art performance, scoring 87.7 JNDF on the DeVos 2017 validation set, 82.9 JNDF on the DeVos 2017 test set, and 86.3 JNDF on YouTube-VOS 2018 validation. Despite employing a less complex memory mechanism in contrast to XMEM, omitting the direct injection of instance information as DeVos, and foregoing hierarchical propagation like DAOT, our method achieves commendable outcomes in both accuracy and notably FPS. This highlights the efficacy of incorporating motion-guided attention to the VOS task. It's worth noting that our research direction is orthogonal to those in DeVos, DAOT, and XMEM, and can further benefit from the ideas presented in those work. As shown by the goldfish sequence, our approach demonstrates superior performance under complex shape and appearance changes. Additionally, the mountain bike trick sequence demonstrates that our design results in strong performance under rapid motion. These findings highlight the effectiveness of the proposed approach in handling various challenging conditions. One practical limitation is that the framework depends on a pre-trained optical flow estimator. We believe, though, that it's quite common that both optical flow and VOS are required simultaneously. Moreover, our approach works with different flow estimating architectures, thus providing flexibility in actual choice. We show strong performance of our method in a complex scene. Summing everything up, we propose DeVos, a vision transformer for video object segmentation that combines memory-based matching with motion-guided propagation, resulting in a stable long-term modeling and strong temporal consistency. To facilitate semantic matching, we employ adaptive deformable video attention, called ADVA. ADVA is an effective sparse attention capable of decoupling motion and query-specific semantic features of a current frame. DeVos L achieves SOTA results while offering competitive FPS.